Hello everyone, hi and welcome you all on Physics Addhyan. So in the previous video we have studied the topic that was kinetic theory of gases. Especially we revised all the important topics from there. So if you have not watched this the previous video, there is an I button on this side will appear, so you can watch it from there. Okay, now let's start the second topic that was the gaseous law of the gas law and the laws of thermodynamics. So the very first law that we know from our class 12th equation, that was ideal gas law, that is PV is equal to N times kBT, or we can simply write it as for n number of molecules we write it as nRT. So PV is equal to nRT, where your capital N is equal to N times Na, the number of moles into the Avogadro number. So this is for ideal gas. If the gas is not ideal, then we have a diagram versus that is a pressure, and this is PV by nRT, and from this diagram we will calculate a factor that is called Z. So Z is your PV by nRT. For ideal gas this factor is 1. So for ideal gas, what would you expect, that there is a linear no, it is a constant response. So this is for ideal gas, and for real gases this response is not linear. For hydrogen atom, for a hydrogen gas, this response is has a negative has a slope with respect to this ideal gas. And for helium gas, there is a low it has a low slope than helium gas, sorry, low slope than hydrogen gas, but it's still this Z factor depends, and I will tell you what this Z factor means. And for other three gases, there are other gases. For these gases the response is quite unusual, so this is response, you can write it as N2. So these are not graphed graphs, I'm just giving for your just for you to know, this is CH4. And for CO2 this graphs like the CO2. Okay, so what the Z factor will tell you, so Z factor can be greater than 1 or less than 1. For ideal this is 1. So if Z is less than 1, this is means the negative deviation. Negative deviation. So what this negative deviation means, that this means that the gas is more compressible. More compressible. And when Z is greater than 1, so this is the positive deviation. Positive deviation. And this positive deviation means that this is a less compressible gas. Less compressible gas. Okay, so that was a comment on the ideal gas and the real gas and how to finding this Z factor. So any real gas can be thought as an ideal gas in the following limit, that is low pressure and high temperature limit. Low pressure and high temperature limit. In this limit, and a real gas can be considered as an ideal gas, because at high temperature all the molecules will be very far away, and at low pressure they will have a very less interaction. So we can consider these are independent of each other, then we can consider as an ideal gas. Okay, so in this particular limit we can say that real gas turns to be ideal always, although it is a limit. Okay, so now this was for ideal gas. We know ideal gas, we know an expression that was PV is nRT. So this was for ideal gas, but there are some corrections in when we have an real gas. So what that corrections are, there will be two corrections. So one is volume correction, and one is intermolecular forces correction. So we considered in ideal gas, we considered that there is no volume to that particular molecule for that particular molecule of that gas. But in reality, there is a volume of any particular gas. So the effective volume in which that all the molecules are uh, having the dynamics, so that will be the number of molecules. Let B be the volume of one particular molecule. So this is the effective volume correction, and there will be all the pressure correction. So this pressure are turned to be proportional to n square by v square, that is a number density. N by v is number of particles per unit volume whole square, so it depends upon that. So your the real gas equations turn out to be p plus a n square by v square. A is just a constant, b is a constant, and v minus n times b is nRT. Okay, n is the number of moles, remember. So this is an expression for an real gas. And there are some quantities that are defined to this, but this real gas system, which we call as critical exponents. Critical exponents. So what that critical exponents are, we draw a diagram versus pressure and the volume P versus V, and there will be a type of maxima occurs. So at that maxima, del P by del V will be the zero, and there is a reason why we are putting this. So since this is just a revision formula, so I'm not going into that detail. So this is called the point of inflection. Point of point of inflection. Point. I'm not. So this is, there was something wrong with my pen. So this is point of inflection. Now it is good. So from this expression, we can find out the critical pressure, critical velocity, critical volume, and the critical temperature. And these, remember these formulas. This is A by 27 of B square. This critical velocity is 3bn. This critical temperature is your 8an by 27 rb. So remember this, because if you are preparing for jam, sorry, for this bhu and du entrance examination, this question is a very often asked question, so they just ask this question. And there is also one quantity that is defined as Boyle's temperature. Boyle's temperature. And that temperature is turned out to be, let me call this is TB. This is the Boyle's temperature. This is simply A by RB. So this is A by RB. Now if I put this equation into uh, so let me find this ratio, PC VC by R into TC. So you convert PV is nRT. So for 1 mole this should be 1, but for this real gas this constant turns out to be, sorry, 3 by 8, 8 by 8. So I think this is 8 PV or 27 8, huh? So temperature will have 8. So this is PV by RTC ratio. So if you calculate this ratio, that's turned out to be 3 by 8. So this was for this particular gas relation. This expression, these expression can be asked for any different uh, gas equation, some other gas equation which follows a different law of equations. Then you have to calculate this del p by del v is 0, del square p by del v square is 0, and then you have to conclude this pc vc tc, and this relation will be different for that particular gas. So it depends upon what law that gas is following. Now there are some related quantities, that is work done and heat of the system, and I will tell you while describing these laws. So let me just quickly come to the zeroth law of thermodynamics. Is very simple, that it not as simple if you really think about it. It shows that if two bodies are in equilibrium with a different with a different system, let A is equilibrium with B and A is equilibrium to C, then we conclude that B is equilibrium to C. It is a very, it is not a very what I say, very easy to understand it. Okay, but for the time being, this is not our concern to be for this particular exam, so I'm not doing it. But when I will be dealing this first law of thermodynamics, I will try to explain the idea behind that of empirical temperature and all that, and it's very interesting. So let me not go into that detail and just describe the first law of thermodynamics. There are various sign conventions which is followed, and this is different from if you have studied chemistry and physics. So they both have a different sign convention. I will tell you what I usually follow. So that is delta Q, that is heat given to the system is equal to work done by the system plus it will increase the internal energy. So if I give a heat to the system, so when you give some heat to the system, what that system will be, so it will do some work, so work done by the system, and it will increase some internal energy. So this U denotes the internal energy of the system, or in differential form we can write it as del Q plus del Q is equal, seems to be not equal to, is equal to del W plus dW, sorry, du. So du is the total derivative of this internal energy, because it doesn't depend upon the path of the system. The internal energy, suppose you have point A and point B. So whether you go from here to here or here to here or go from here to here, this path 1, 2, 3, the internal energy, the difference in internal energy between A, P is independent of path, whether you go from 1 to 1 or 2 or 3, whatever path you choose, that is independent of path. So it's thereby we generally write it as total derivative of this uh, internal energy, whether the work done and the heat given to the system is dependent upon what path we choose. And if you, in many of the graphical problems, you will use this concept that du for a cyclic coordinate du is 0, because if I go from A to B and B to C and C to D and then again D to A, then I am again at my initial position. So my total change in internal energy will be 0. Then we will be calculating this quantity del Q minus del W to be the constant. Okay, and this du, that is the specific the change in internal energy in terms of specific heat, we can write it as dt. So du is Cv times dt. And if I talk about in the term of external pressure, then this du can be written as del q minus del w, where del w is the work done by the external pressure. So this we can write it as minus p times dv. So this is du is this. Okay. Now, let me talk about some specific type of processes that can happen. So first, I will talk about the isothermal process. Isothermal process is where the change in temperature doesn't happen. That if the process is isothermal, then then the difference in temperature at different points will be zero. It means that both the points in the system has the same temperature. If delta T is to be zero, then dq will be, or specifically del q will be del w, because your internal energy is a function of time, temperature. If so, u is generally a function of temperature for ideal gases. For real gases, this internal energy may depend also on some different functions. So in isothermal, I will write the define a quantity, that is work done. Work done is the integral of P into dV. If you calculate this expression, you will get nRT log of V final by V initial. This quantity you can also write in terms of pressure. This is nRT log of P initial versus P final, because P is inversely proportional to V. So VI and PI just are opposite. Okay, so this is the isothermal process, and you can calculate a quantity that is called the work done. Then there is a quantity that is isochronic process. So in isochronic process, what happens, the change in volume is zero. So at two different point in the system, the change in volume is zero. It means they have the same volume at that different, the pressure may be different, the temperature may be different, but the delta v is zero. It depends upon the system. So in this particular type, your this PdV, work done, is zero. So your internal energy is equal to specific heat, the heat transfer to the system. So in, and you know that dq can be written as cv into dt. So this is for this particular this particular process, your du is equal to dq is cv dt, and in this process your work done is equal to 0 because it's pv dv and dv will 0. So this is work done is 0 for this particular process. Okay, now let's talk about the next process, that is isobaric process. Isobaric process. So what that isobaric process is, where the difference is pressure is 0 along that process. So if I write dq to be du plus pdv, and one more thing, in this isochronic process, if your delta V is 0, it means volume is constant. Then for ideal gas, P by T, pressure by temperature is your constant. Let me write it as K as a constant. So isobaric process, dq is defined as du plus pdv. There is no change in the system. And you can rewrite this quantity dq, that is cp dt, that is a specific heat at constant pressure. Okay, so because this is a constant pressure process, so you can write cp as dq by dt. And in this process, when pressure is constant, you can write v by t to be the constant quantity, or you can call this as some constant k. Then there is one more process which is much often asked, that is, let me write this as fourth, that is the adiabatic process. In adiabatic process, what happens? No heat is exchanged. Delta Q is equal to 0. If delta Q is equal to 0, then du is minus times PdV. And there are some more relations. Let me just quickly write that pressure P into V ki power gamma. Gamma is your Cp by Cv, which we have defined earlier. That is your constant. The second point is your, you can just manipulate or just play around this equations. You will get three different relations in p, v and t. So I'm just writing them at once at one particular place. So your t ki power gamma p ki power 1 minus gamma, this is p, is equal to constant. So this is just, sometimes you have to given a pressure, a volume, and you have some different monatomic diatomic gases, and if I increase the pressure adiabatically or lower it by half, what will be the volume and what happens to the temperature. So you can calculate these quantities from here. Now let me define a quantity, that is work done in an adiabatic condition, because these work done will be very helpful when we will be studying this what that call is Carnot engine process, ideal engine process. So there we will use this equation. So work done in this process is nothing but initial volume pressure, initial volume minus final volume divided by a factor, that is gamma minus 1. You can also write it in terms of ideal gas equation. This is T initial minus T final divided by gamma minus 1. This PV is equal to nRT, just I have used that equation. So this is the work done, and this is the adiabatic condition where the heat exchange is 0. So this is important. Now one more process can be happened, that is called the cyclic process. In cyclic process, what happens? We came back to the initial position from where we started. So it means delta u is 0. As we have discussed, that delta u is a path dependent quantity. So again, if I have a2, I have went to b to c to some other quantity d, then e, and then we again come back to a. So that is called a cyclic process. In this cyclic process, delta U is 0, so it means work done and the heat given to the system are same. Okay, so that is the expression for your cyclic process, and this is for in numerical purposes. The cyclic process and adiabatic process and the isothermal process are the most used processes in this particular topic. Now there is one more quantity, that is not quantity, but the some questions has been asked on this topic, that is called the free expansion of gases. So what happens in free expansion? No heat enters or leaves the system, and no work has been done by the system or on the system. So when no heat enters, my dq is 0, no work done, my dw is 0. It means in free expansion, your total change in internal energy is 0. So this is the most important concept. So free expansion, no change in internal energy. So this is no change in internal energy. So in free expansion, this is only the concept that we have done, that there is no change in internal energy. Now, let's see for ideal gas. For ideal gas, we have this du is Cv times dt. For free expansion, your du is 0, the change in internal energy is 0. It means that your dt is 0. So in free expansion, you have, there is no effect on temperature. The temperature will remain as it is. So if dt is 0, then the effect on temperature due to free expansion is 0. There will be no effect. But in case of ideal gases, there is effect. And what that effect is, let us study. So in real gases, you have studied that internal energy is just a function of temperature. But for real gases, it is also a temperature of volume. So I don't know whether you have heard about this or not, but it is. That internal energy is a function of temperature and volume for real gases. For ideal gases, it is just a function of temperature. So if I write the expression, then du is dq minus p dv. So let me differentiate this equation with respect to volume. So this is, you can write du by dv. So this is du by dv is equal to, by the second law of thermodynamics, we can have a concept of entropy, which says that dq is my T times ds, where ds is the change in entropy. So this you can write it at T into ds by dv at constant minus p. Okay, at constant volume I am taking this derivative, du by dv. Then there is a Maxwell's equation exists, which says that du by dv at constant. Oh, I'm sorry. This is for temperature. So we was taking the differentiation with respect to not volume, because the temperature is constant. So this was with respect to constant temperature. So del S by del V at constant temperature is del P by del T at constant volume. So this was the expression. So I can write del U by dV at constant temperature is equal to T into del P by del T at constant volume minus pressure. So just look at this quantity which I have calculated. What this quantity will tell you how the internal energy varies with respect to volume. So this will tell me delta U, that is change in internal energy with respect to volume. This is the first quantity. So there was two quantities. U depends on temperature and volume. But as a whole, if I'm talking about the cyclic process, then delta U due to the whole gas should be 0, which has two quantities independently, that is delta U due to volume, this volume of the gas, and delta U that is due to the temperature of the gas. This should be 0. This implies that delta U due to the temperature is equal to minus delta U that is due to the volume part. So let me evaluate this quantity. So this quantity is delta U of volume, and this delta U of volume can be evaluated from delta U of temperature. So I will calculate the temperature part, and that will be the negative of it will be due to the volume part. So from the previous expression, it is same that delta U that is due to the temperature is my Cv dt. So my dt will be delta U of temperature divided by Cv. So if I know what is a contribution due to the temperature, then the same contribution will be due to the volume in negative sign. So the overall uh, internal energy is zero. The change in internal energy is zero, but there are two different components that are cancelling each other. One is the internal energy that is increased due to the temperature. So it will have a reverse factor, which will, if delta U increases due to the temperature part, then delta U due to the volume, that will decrease. Okay, so these are dependent on each other. So what happens at the end result? So this was just to tell you that there are two different side-wide component, and from detail analysis you will get to know that delta U of volume is greater than zero. This implies, means if this quantity is greater than zero, then this should be less than zero. So delta V due to temperature is less than zero. Sorry, delta U. So what does it mean that temperature will fall? Temperature will fall down. So in the ideal gas, what we have seen that there is no effect on temperature, but in real gas, the temperature will be lower than when the earlier voltage was. Now there are two different kind of processes which we have discussed. That was isothermal process and one was adiabatic process. So in isothermal process, we can write this quantity dP by dV as minus P by V, and adiabatic process we can write dP by dV is minus gamma P by V. So this quantity gamma, we can define it as, so these expressions just came from the previous the expression which we have defined for pressure and volume. So this gamma turns out to be dP by dV of this adiabatic process divided by dP by dV of your isothermal process. So dP by dV is the slope of P versus P, dP by dP is slope of isothermal, and gamma is always greater than 1. So we can say that the slope of the adiabatic process is always greater than the slope of the isothermal process of pressure versus volume relationship. So if we have a pressure versus volume relationship, then if I have given two different slopes, let's see, this is one process and it is not smooth, but let me make it a little bit smoother. So two processes A to B, and that goes from A to C, and you have to identify that which one is which process. Then just look at the slopes. AB has a low slope than AC has a greater slope. So this is adiabatic process and this is your isothermal process if this was happening. Okay, so this is just to identify that which how to identify the processes is given in P and V diagram. So this was for isothermal and adiabatic process. Let me define three more quantities in this particular video and then I will stop it. This is bulk modulus. Bulk modulus, or it is also called the incompressibility factor. Incompressibility factor. This is called to be, let me denote this to be as K. So this K is defined by minus del V del P by del V with constant temperature. So this is how the pressure is varying with volume and multiplied with a factor of volume. So this is the bulk modulus for ideal gas. Now you can calculate this quantity is ideal gas, that K turns out to be the key. Just use the expression PV is equal to nRT. For real gases, your K turns out to be RT. Use the real gas equation P minus AV square by N square multiplied by P minus NB is equal to nRT. Use that equation. When you differentiate it, do all the calculations, then you will be getting this expression. This is volume. This is your isothermal compressibility or the bulk modulus. The second quantity which we often define is isothermal compressibility. Isothermal compressibility. Just don't follow these expressions like K and I'm using this as beta in questions. There will be using some different notations. So you have to remember these words, not these K and beta. Okay. So this isothermal compressibility beta is defined by minus 1 over V del V by del P at constant temperature. So this is how the volume is varying with pressure. Now for ideal gas, again this turn out to be beta turns out to be 1 by pressure, and for real gases this beta turns out to be 1 by RTV, just opposite of what we have done earlier, minus 2a by v square. And there is one more, just remember these three quantities. These are very important for finding some quantities which you will learn when which you have already learned if you have studied this concept. So that is coefficient of volume expansion, coefficient of volume expansion. So you have studied that if you give a temperature to a material body, then its volume will increase or its length will increase. So that's the same coefficient. So this alpha is 1 by V del V by del T at constant pressure. For ideal gas, you can find this alpha to be a proportional to 1 by temperature. For real gas, you can find it out what it will be. So I think this was the main content for this ideal gas and the law of thermodynamics. In the next video, what I will be talking about is the following topic, that is Carnot engine and the entropy. That is the second law. That is the second law. So in the next video, I will be talking about Carnot engines and the entropy and or the second law of the thermodynamics, and in the upcoming videos we will be talking about thermodynamic potentials and phase transitions and all that. So if you like this video, just give a thumb up, as you all know, because that gives us a feeling that you are watching this content and you are liking this content, and do share it with your friends who are giving to take the jam and just examination, so that they can also have a pre-look, pre-visit to the important topics and just important formulas, because we generally don't remember all these. So do your preparations very well, and thank you very much for watching this video. Thank you.